Let's take a look at one of these miracle power-saving heaters that is being hyped as being the most efficient way to heat your house. Buy one now, lots of marketing. In reality, these things are rated 500 watts, which means that if you're comparing it to a standard 2 kilowatt heater, they're both 100% efficient in conversion of electricity to heat. But this one is a quarter of the power, so it'll take 4 times as long to heat your house. That's basically it in a nutshell. But let's explore it, and we'll open one of these up. We'll take a look inside. I've actually got two here, and this one has failed. This one is rated for higher power, and oddly, while this one has a little on-off switch at the side, as well as the electronic controls, this one also has the electronic controls and an on-off switch again. But I was wondering, is that killing all the power to unit? Because it is rated almost a kilowatt, this one. And it turns out, yes, it is, because that's the first thing it failed was the switch. I shall explore that later on. This is the most fashionable one at the moment. And this one was bought locally, actually. It wasn't bought from an online seller. Let's plug it in. So I'm going to plug it into the hoppy. And I'm going to flick the little switch at the side. It is already on. So I'm going to use the little button here to start it, and it is displaying very dimly. It says 30 in there. I think that's 30 degrees Celsius. Initially, the power it draws isn't hugely massive, but then it starts going up. It's gone up to 690 watts. Now it's settling back down again. 600 watts. It smells quite dusty, putting out a fair amount of heat, and it's going to settle down roughly about 500 watts. My hand is getting very hot here, holding it in front of this to try and shield the microphones. So 0.99 power factor, it's very efficient and it's very hot. Right, tell you what, I'm going to press this button again, and it will now go into a cool down cycle, and the display in here, I don't think you can even see it. Well, tell you what, let's turn off the light so you can see it. Here we go. It's dark now, and you can see the countdown sequence that's going on. What it's doing now is it's blowing cold air to allow the heater plates to cool down, because this is a solid state heater. What they like to call a ceramic heater. Right, tell you what, I'm just going to pause momentarily while it finishes its cool down sequence, and then we shall continue with the exploration. The light will be coming back shortly. Mind your eyes. It has cooled down. It is time to do our exploration. So I've got my non-VDE compliant screwdriver here that I've cut the insulation off just to allow it to actually reach things that screwdrivers are supposed to reach. As you can see, this is the square pin British version. It's pretty clear from this little plastic tab down here that it's designed to take multiple styles of plugs that just clip onto some pins or something in there, I'm guessing. We'll find out when we open it up. There are 4 screws holding it shut. And what am I expecting to see inside? Possibly a little switch mode power supply for the display and the fan. And then possibly a circuit board with a relay. Well, definitely a relay. I could hear it clicking. This isn't coming out. Is it because I've not unscrewed all the screws completely yet? I think they're more or less unscrewed. Or is it because there's more screws down here and they need to be taken out too? Yes, that's probably it. I'm going with that as the reason it wasn't opening too easily. Just as well I didn't go straight into the brute force mode. Oh, I can feel it falling apart now. Off comes well, it's just kind of opening up like this. Well, there's the control circuit board. There is what is that? Oh, it's a little light underneath. I didn't even know there was a little light underneath. Does that unplug? Does it unplug? No, it's not unplugging. Right, okay, that's a little night light feature apparently. How pointless. So what do we have? We've got the control PCB and the power. There is the switch mode power supply. Well, tell you what, I shall whip the circuit boards out. We'll take a look at the circuit boards in closer detail, and then we'll take a look at the heating element itself. One moment, please. Reverse engineering is complete. Let's resume. So we have 2 cards as previously shown. One is the power card. It's got the power supply on it. It's got the relay for switching the heater, and it's got the transistors that switch the output to the fan and the relay. The control card has a thermistor on it and a little microcontroller. It's a standard microcontroller. It does actually have a number on it, and it's to use the smallest microcontroller possible. They've multiplexed the displays and the buttons. It's very, very minimalist, but I shall show you the schematic for this. In the unit itself, we have a fairly standard 12-volt fan, DC brushless fan, DC 12-volt, 160 milliamps. And then in the unit itself, the incoming supply, live and neutral. Neutral goes straight to the circuit board where it's just a common connection bus for the heater. And the live goes into this little switch on the side, comes back, goes through a secondary thermal cutout here, bimetallic cutout, and then it goes up to the circuit board where it gets marshalled down to the heater, which has 3 connections. The middle connection is the neutral, and the 2 outer ones are linked together and they're live. What that means is this metalwork in here is live. The central area is neutral, outer area is live, and these little ceramic plates in here are the heater devices. They are classic PTC heaters that self-regulate. The hotter they get, the higher the resistance goes, so they just sit at a nice equilibrium level. And as the air is blown through this and it takes it away, they will then sit lower in resistance to actually maintain that heat. You could say that someone could poke things through the front of this grill and touch the live connections, but the same would happen with an ordinary heater with 240 volt or 120 volts on its heating elements. This has just popped out. I wonder if it's directional. Who knows? Anyway, let's move on to the schematics, because they're the interesting bit. We'll start with the power marshalling card. So I'm going to zoom down onto this, focus down onto that. We have the common neutral connection here. We've got a fuse for the whole lot. We've got a metal oxide resistor, a class X2 capacitor. This is inverted, by the way, just so it makes sense compared to the actual circuitry on the other side. It makes it easier to reverse engineer. We've got some filtering on the secondary side and the DC side. With brown, black, red, that's 1000 microhenries. Feeding a main smoothing capacitor, the chips in the back with its little transformer and a bootstrap capacitor. This capacitor is the one that powers the chip itself. It's got electrical separation. I don't know if it's needed. It's a double insulated appliance, but they've done it. That will depend on the separation of this transformer. On the output, there is a biggish capacitor for the 12-volt supply, the relay, primary, and coil chassis, and then there's a little capacitor here for a 5-volt supply before it sends 5 volts and 0 volts out to the other card, and also has 3 signals back: fan high, fan low, and heater. Looking at the back of this is where I went a bit further than I should have. We have the switchboard power supply. There's the rectifier, switchboard power supply with support components, snubber network, feedback and bootstrap circuit, and the sense. The pink indicates the sense. So it's set by sensing the voltage in the feedback winding, it can monitor the voltage in the secondary winding. Secondary winding goes via diode to that capacitor, and then there's a 5-volt regulator here, and the transistors that switch the fan, but also one of the transistors switches via a stack of 10 ohm resistors. 2 10 ohm resistors in series gives 20 ohms, but there's 2 sets in series in parallel, so that goes back 10 ohms, but they've spread the dissipation across them. Quite an odd arrangement, wasn't expected to even have fan control. There are snubber diodes across the coil and the fan. Oh, there's also an output, bizarrely, with its own resistor here for the LEDs. I show you that in the schematic. Here is the schematic. Now, initially, I've just abbreviated the PSU into a block marked PSU, but I have reverse engineered it. So the incoming supply comes in via that fuse. There's the relay contact. They've called it K1, so I've marked K1 as well. There's the coil for it. There's the switch for it. And there's the PTC heater. I'll just write PTC, positive temperature coefficient. The hotter it gets, the higher its resistance gets, so it self-balances. Keep in mind, this is not a bridge rectifier. This is a whole PSU. I've just drawn it with the AC in, the plus minus out. It looks like my bridge rectifiers. Here is the bizarre LED circuitry. There's a couple of LEDs just point down the way. They're blue, they're pointless. It's got a 1.5k resistor, and ideally what they'd have done is then they'd have just basically had 2 LEDs in series like that, because they have 12 volts. and the LEDs are just blue LEDs, and they would have just gone like that, and it would have gone to ground, and that would have been it. But instead, they've put the two LEDs in parallel with their own resistors, so that's bizarre, and that's strange. There's a 10 ohm resistor feeding a 5-volt regulator, and that just puts out, it's got decoupling capacitors and also a smoothing capacitor, and then puts 5-volt out to the main logic circuitry. But there is also a smoothing capacitor on the main logic circuitry. The signal's back, so it's putting the 5 volts out, it's putting the 0 volts out to the on that connector to the control board. The signals it gets back are heat, low and high. The heat turns on this standard NPN transistor, which brings on the relay with its little back EMF spike suppression diode. And then the low and high for the fan also has its back EMF spike suppression. High just couples the fan directly across 12 volts directly. The low puts the 10 ohm resistors in series, so that if this transistor turns on, the fan will run at lower power, as opposed to that one. It's just probably to keep the noise down. The power supply, let me just show you the power supply for completeness here. Incoming supply to the power supply has a metal oxide varistor, or VDR, voltage dependent resistor, and a 100 nanofarad capacitor for noise suppression. It's got a bridge rectifier, it's got an inductor with a resistor across it, presumably to damp resonance, and then it's got the 6.8 microfarad 400 volt death beam capacitor. That's that big fat juicy capacitor there. There is also another 6.8 microfarad capacitor, but only 50 volt, and that is for powering the PSU chip, and that has a number OB2512NJP, and it's being used fairly textbook in this instance. So initially, when you turn it on, current passes through these two 1 megohm resistors and charges that capacitor up to the point the voltage is high enough that the power supply chip kicks in. When it does, it starts pulsing the primary winding down to the 0 volt rail via this 1.8 ohm resistor, which it uses for sensing the current through it. When it turns off, the magnetic field that it's built up collapses, and when it collapses, it puts current out through the secondary winding to the 12 volt output via this diode, and it will be a high speed diode, and that capacitor 470 microfarad, 25 volts, but also it puts out the feedback winding through this resistor and diode to charge the capacitor up, so it then powers itself. But it also uses that winding via a resistive divider and a capacitor for filtering to monitor the voltage that it sees. Well, by monitoring this voltage, that's why it's a very specific resistor here, it can actually determine what voltage it is on the output side as well. The other bit of circuitry here is the snubber across the primary. When the primary, the MOSFET in here, or stand transistor, probably a MOSFET, turns off, before these diodes turn on, there is a slight spike of the collapsing field, and that is clamped to protect the MOSFET in here and potentially to protect other components as well. So that spike gets diverted via this diode and this resistor to this capacitor, which just absorbs that tiny spike, and then this resistor here just discharges that capacitor slowly, just to prepare it to catch the next spike on the next cycle. That is it in a nutshell. That's it all completely covered. Right, next bit of the circuitry, next bit of the puzzle is the logic board. Let's take a look at the logic board. The logic board has two 7-segment displays on one. Well, it's got one display with them multiplexed. It's got 7 or 8 segment lines plus the 2 control lines. I don't think it's using the decimal points, not sure. But to keep the pin count down, they've also multiplexed the switches in those. It's quite odd. So the power comes on, there is a little small electrolytic capacitor here, 100 microfarad, 16 volt, to provide stable current to the microcontroller, which is under here. And there is also a connector here for the thermistor. The thermistor is actually just stuffed. It's stuffed down this little port here. I don't even know if you can see it, but this little port here, and there's a little pinhole here, but it doesn't really go out there, so it's just ambient. It's more or less sensing the temperature of the case. I would guess that's a 10K thermistor. Hold on, let me, yeah, that's set to 20K, that's handy. Let's just double check and see if we can get a reading off that. If it's below 10K, or around about 10K, that will be a clue. Yeah, about 9. Yeah, that's about as good as you'd get. That's fine. That is fine. It's a 10k thermistor. That's a very common thermistor. What that means is roughly 25 degrees Celsius, I think it is. That's what resistance this little bead thermistor will be. If we look at the circuitry in the back of this, we have the chip F1202AMBN. We have the incoming supply positive and negative here, the smoothing capacitor here, the thermistor is connected positive, then forms a potential divider with another resistor to negative, and then has a little filtering circuit before it hits the microcontroller. There are loads of 100 ohm resistors, limiting the current from the output pins to the segments, but also to, they've got more than just 7 or 8, they've got about 9 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, that they're also protecting against the button presses, shunting matrices, lines together. And there's also diodes for that in the switches. If you look up switch matrix with diodes, you'll find what I mean by that. I didn't draw that out in the schematic. Let me bring in the schematic, which I abbreviated a bit just because the switch matrix was just going to look messy. But here it is. The incoming supply comes here, 5 volts comes in, there's the 100 microfarad capacitor, the decoupling capacitor local to the microcontroller, there's the temperature sensing, there is a 10K, NTC, it's almost certainly NTC, negative temperature coefficient. As the temperature goes up, the resistance goes down with this one. And it's a forming a potential divider with a 10K resistor, and then there's a 1K and a capacitor just to filter that before it goes to the microcontroller. The microcontroller's outputs are a direct link for the heat relay and a separate, there's an extra 1K resistor to the fan high and low. I think they've done this, they've used these resistors as little jumpers just, or it's a universal circuit board. I would have thought that they might also have had a resistor on there if they were doing that, but they haven't. The display is just all the rest of the lines from this. Driving with 100 ohm resistors driving and diodes driving the segments and receiving the button inputs as part of the scanning. It's all very logical. I mean, that processor won't really be stressed too much. It's not doing an awful lot. Its most work will be scanning the LED displays, but there's only 2 of them, so that even that's not going to be too hard. And that is fundamentally it. That's the whole thing reverse engineered, except for the LEDs and the diode matrix. Right. Now, I also said, right, I'm going to have to find that now. One moment, please. I have found it. This is the other unit, which will be very similar but slightly higher power, and I can see that it does have more sections of the PTC heater elements. So I shall whip the screws out of this one, because I said I was going to take it apart. Really, I should have taken this apart in a separate video, because otherwise this video is probably going to get quite long. It's taken a long time to reverse engineer that. It always does. I didn't mean to go so far, but I did. This one has a simpler display. It's only got 3 buttons. It does have a display though. I wonder if it allows fan speed control. There was a remote control with this one. I dropped the remote control into my pile of stuff and it's never been seen since. It'll probably surface at some point. What is this one going to be like? It's got, oh, that screw there needs to be taken out a little bit more. It's got a nicer construction in the sense that the front comes off sensibly. Are these supposed to be all black and unpleasant looking? I think so, not sure. So we've got 2 connections. Oh right, it's just used blue as links. So it goes live, neutral by the look of it to power those. There is what looks like a triac to switch the heating here in this one. There is this little switch which I'll wager is dead because that is the most likely candidate for failure. Let me just grab my continuity tester and we shall probe that. Maybe it will beep, maybe it won't. Yeah, it only works while it's being pushed in. It's screwed. That's a surprise. I mean, seriously, passing how much current through that? It's 900 watt, passing about 4 amps through one of these dinky little switches. Imagine that feeling, what a surprise. This one is the same sort of arrangement. It's got the buttons on here, 7-cent display. It's got the same size of chip. What is the chip? Is it marked? No, it's an anonymous chip. This is a generic Chinese one. Not many connections. Well, it's got 5. It's got the same number of connections, really. Oh no, everything's fallen to bits. This is just so much simpler. And it's got a little infrared receiver, which the other one didn't have. And its power supply. It's got an inductor in there, so it's using a buck regulator. This is definitely the cheaper of the two. The other one looks quite good quality. This one is not good quality. Well, the switch is an indication of that. But that is it. This one isn't bad inside. There's a few design quirks. But on the whole, it's not too bad. The circuitry is fairly logical. It's been done textbook style. So, to be honest, this one, it certainly, as I said right at the beginning of the video, ignore all the advertising. It's not going to exclusively heat your house. But I use one of these under my computer bench because that's when I'm least active. And when it's cold in winter, my fingers will get cold at the bench. It just warms the bench and gives a warm upflow of air from it. So that's all right. So, on the whole, this one I think was bought locally. And it's pretty good quality.